Hello, very good afternoon to all of you. So, first of all, I would like to introduce myself. Myself, Anil Kumar Sharma. I'm from Impulse Technology, Delhi. So, this Impulse Technology is basically technology software providers. So, today's sessions, my engineer, Mr. Ujjwal Pratap, he will deliver the talk on very innovative softwares that is called quantum tickets. So as everybody knows about the quantum is the upcoming futures in this domain, technology domain. So this hands-on session will help you a lot. And we have also given the licenses, the installations procedures, as well as some installations videos. So many of participants have already downloaded and installed. Those who have not downloaded yet, not installed yet, don't worry. We will also help you after this workshop or end of the sessions. We will help you to install the softwares. License duration will be 1 month. So anytime you can also get the access of technical support on using our softwares. First of all, my colleague Ujjwal will give a small presentation about quantum ticket software, and also he will deliver about the how to install this QTCAD software in your computer, and then live hands-on session will also be delivered. So being a beginner, you will understand a lot of things. So I request all the participants, if you know someone's, kindly invite other participants as well, so that everybody will get to know the innovative software, specifically for semiconducting devices, spin qubit devices, superconducting technology device simulations. Now I would like to hand over my session to my colleague Ujjwal. He will deliver the small session to you, and as well as the practice. You can also make the practice. So be patient, keep concentration to attend this training session, and then later on, if somebody is more interested in the product, then we can also discuss on the further deep insight about the product. So thank you for joining all the session, and please stay tuned and please give your attention to our hands-on session. Thank you very much. Now, Ujjwal, please continue our session and give the insightful talk on this product, please.
Okay, thank you, sir. Good afternoon, everyone. I welcome you all to the two-day hands-on training workshop on QTCAD software organized by Impulse Technology. Basically, in this session, we will explore how advanced simulation tool like QTCAD can help design and analyze your quantum and nanoscale device efficiently. I am Ujjwal Pratap Singh. I am excited to guide you through the journey of world of next generation semiconductor and quantum technology. Before moving to the PPT part, let me brief about our company, who we are, who are partner and customer. Impulse Technology is a distributor of DFT-based software, solar cell, and quantum technology software. We are partner with two companies. First one is Nanoacademic. Nanoacademic is a Canadian-based company which offers several software for nanomaterial and quantum. You can see first one, Nanodeckel. Nanodeckel is a DFT-based software which is based on density function theory plus non-equilibrium gain function. And it is used for the material and device simulation both, where you can find the transport properties also, quantum transport properties, IV characteristics, and material properties also, like band diagram and PDOS, LDOS, and other parameter also. Second software is Rescue. In Rescue, it is a material-based software which is based on density functional theory and density functional perturbation theory, where you can find the optical properties, Bonon properties, Raman properties, and other parameters also. And you can find analysis like density of state, band structure, and you can use HSC06 and other exchange correlation function. And third one is QTCAD. We will know more about in upcoming slides. And second company is Fluxing, which is a Switzerland-based company which offers several software for the solar cell. You can see first ones. The first software we're talking about is a DFT-based software, which is a Nanodeckel, which is based for the density functional theory and non-equilibrium gain function, where you can find the transport properties and other material properties also. And the second software is Rescue. Rescue is based on density functional theory and density functional perturbation theory. where you can find optical, Raman properties, phonon properties, and other parameters also. This is GUI where you can create your material file and simulate also result in the for a TFT based software. You can find the photo current and effective index transmission. And second software we're talking about the set cost for solar cell. You can see the interface and you can find external quantum efficiency. If someone working on the solar cell can also give trial version for this software also. And here you can see the law software where you can find the electrical module plus thermal module and optical module. Where you can find the characteristics related to the thermal module, optic module, and electric module also. And you can compute IV curve for the large devices and geometry of the electrodes and device operation. Let's talk about the QTCAD software, our innovative quantum design tool, QTCAD. Quantum technology computer-aided design for a quantum technology hardware, where quantum technology design is a finite element matter simulation, and it also comes with the atomistic modeling capabilities. You can see it's our advanced spin qubit modeling tool. And when you talk about the feature of QTCAD, it comes with the electrostatic tool that solve the confining potential of quantum dot in semiconductor nanostructure and find corresponding envelope function for electron or holes. Basically, its purpose to solve how quantum dot confine electrons or holes in a semiconductor nanostructure also, and it calculates basically confining potential, which is like energy trap for the particle in quantum dot. And we talked about the second feature. It comes with value splitting calculation tool, where you can compute the energy difference between quantum states in silicon-based devices and other parameters also, and help calculate the splitting between values also. And the third, an exact acceleration tool for the treatment of Coulomb interaction, and where you can find the critical for a silicon qubit stability and simulate how electron treated with each other in a Coulomb forces and analyze few electron system by solving equation to predict how electron behave in a quantum states. And we've talked about the fourth one. It's a master equation solver for a transport calculation where you can calculate how electron move when tunneling occurs and simulate the sequential tunneling regime and where electron pass through the quantum dot one by one. And QTCAD come with a cryogenic temperature where you can simulate your device and nanoscale devices at cryogenic temperature. Many TCAD will not offer the cryogenic temperature also, cryogenic temperature supports, and it also come with the Python application programming interface to launch the simulation. And it compatibility with the device then, which is an open source Python API created by the Nanoacademic that define gated quantum dot geometry from a GDS layout. You can give the input as a GDS layout file and it create a heterostructure and it take mesh as the input and run the simulation. If we talk about the technological background in spin qubit in semiconductor, it basic principle how to confine the electron or hole in gated quantum dot in semiconductor heterostructure and find the spin degree of freedom to implement qubits and manipulate the spin with a microbit and how interaction like find the two qubit gate by exchange interaction. You can also see in the diagram in heterostructure how to confine the electron or holes. And if you talk about the technological advantage, it is small nanometer size and is able to fit million of qubit on a single chip, and it operated at a temperature of 1 Kelvin, and you can leverage the manufacturing capability of the semiconductor industry also. You can see the company with also spin qubit devices activities like Intel, Global Foundries, and Equal1, Direct, and other company also you can see, which company which interested in the spin qubit R&D activities also. If you talk about our innovative quantum design tool, it's basically for the confined like to electrons or holes and difficult to make qubit from a confined electron and study a large set of devices until finding the desired property in money and time also you can see. You can design like a specific particular devices in time. And basically, our value proposition to design the process with reliable all-in-one tool like spin-based quantum component in laboratory condition, like at cryogenic temperature, and other also like adaptive meshing and other features like NEGF, tunneling occurs, qubit modeling, atomistic, and tight binding also for advanced communication solution, and you can security and quantum computing devices. If you talk about the difference between TCAD and QTCAD, TCAD basically based on semi-classical physics, and you can see quantum technology computer. It's based on quantum physics, and it comes with the nonlinear Poisson equation solver, Schrodinger solver, and you can find confinement potential also for the quantum dot and spin qubit devices, superconducting qubits, and you can find the performance metrics also as compared to the TCAD tools. Basically, when you talk about the main challenges of spin qubit simulation, when you talk about the earlier transistor devices, you can operate at 300 Kelvin and many electron occurs and quantum confinement correction, no quantum superposition or entanglement. But if you talk about the spin qubit, cryogenic temperature operation and few electron regime, ideally one or few per qubits also, and it comes with the quantum confinement, superposition, entanglement, and other operation principle also. But when you talk about conventional ticket software, it's not suitable to the quantum hardware design. That's why where QTCAD comes. If you talk about the benefit of QTCAD software, here you can device layout to the qubit performance metrics like Python-based device generator, where you can take GDS file and give to the device end, where you can create a heterostructure and you can create the mesh, and it will give input to the QTCAD simulation, where you run the simulation and analyze your result also, and like calculate the spin qubit performance metrics before manufacturing of your devices. And it comes with the adaptive meshing, like automatic adaptive meshing algorithm, where most convergence occur and robust convergence at cryogenic temperature you can see, and quantum mechanical model. It also comes with quantum mechanical models to essential to predict spin qubit behavior, like for non-linear Poisson equation and other parameters. And if you talk about the features of QTCAD, here you can see cryogenic temperature electrostatics. You can simulate your devices at cryogenic temperature at electrostatics. And it also comes with a Schrodinger solver based on effective mass and KP solver. And it comes with an in-body and master equation solver for the charge stability diagram. You can see the second features like value coupling, advanced spin physics, where you can find spin orbit coupling, magnetic effect, orbital and Zeeman operators, and electron and holes, quantum well physics, and Rabi oscillation, where you can find electric dipole speed resonance, predict Rabi frequency, and leakage from the device geometry, and input magnetic field also. It also comes with the tunnel coupling and exchange, where you can use the quantum transport bits and find the barrier gate control of the tunnel coupling and other parameters. And it also comes with the non-equilibrium key function, where you can find the quantum transport properties like IV cup and other parameters also with adaptive integration to robust convergence. And it also comes with the feature like point charge effect, labor arm matrix solver, strain solver, and it also supports Jupyter notebook and many more to come. If you talk about the another feature, it comes with a tight binding model for a value splitting. It means you can simulate at the atomistic level also, and you can find from atomistic to the device to the qubit and superconducting circuits also. Like superconducting circuit you can see here. If you talk about the QTCAD model, how it works, first we create a device geometry from open GMS software, gate layout from the layout file, and the heterojunction design rule from a Python API, and more complex 3D geometry from the GMS. QTCAD take as input from the two software. You can take GMS and create a mesh file, and second one is device end, where you can take GDS file and it will give the mesh file and give input to the QTCAD software, where you can find the electrostatic properties like define boundary condition and doping intensity and solve nonlinear Poisson equation And after that, you can use Schrodinger solver for effective mass and envelope function, lever arms, and many body solver, where you can find the Coulomb interaction and many body function. And after that, you can move to the quantum dynamic features, where you can find the Hamiltonian corresponding to the realistic device geometry, and find the matrix element of a perturbation to the control field or noise also. And you can find Ravi oscillation, ADSR also, and gate fidelity. And it comes with the transport feature like master equation solver and gate transport fix charge stability diagram, including Coulomb blockade also. You can see the use case of a QTCAD software. Many company uses the QTCAD software to simulate the quantum devices. You can see lever arm extraction in global foundry devices, where it use the QTCAD to form the lever arm extraction. You can see. You can also move to the link to see the paper also. Here you can see the paper also. Common mode control and confinement. Defined quantum dot in CMOS process. And basically, they demonstrate the feasibility of simulating quantum transport and properties also using QTCAD software. Second use case, you can see tunnel coupling and exchange of a germanium double dot devices, where you find a barrier gate control, symmetric plunger gate control, you can see here, and with using the self-consistent equation and Schrodinger Poisson solver. If you talk about the third use case, you can see tunnel coupling variability and the point charge effect in FDSOI. You can see the back gate voltage and the paper also, you can see. The fourth use case, you can see single qubit control to the micromagnet ADSR. Basically, ST Microelectronics use the QTCAD software to simulate the result. And you can see the correlation with ST Microelectronics to find the magnetic field and using the side gate and simulate Ravi oscillation and leakage also. And the fifth use case, you can see charge stability diagram, where we find the electrostatic potential, then energy level, and quantum transport properties at 7 millikelvin simulation. You can see at cryogenic temperature with the defect and the ideal also. You can see the dopant and ideal properties. And the sixth use case, you can see the electrostatic of sextuple quantum dot array. You can see conduction band is simulated with QTCAD software. We also simulate conduction band in hands-on training with QTCAD software. Here you can see the heterostructure with quantum dot array at 700 millikelvin. You can set temperature also in QTCAD software at user requirement. You can simulate your result also. It also correlation with equal one to simulate the result. Here you can see spin qubit in semiconductor mounted 6 qubit quantum computer. In equal one, you can see silicon germanium head structure quantum dot array. Quantum chip simulated with QTCAD software, you can see. And the seventh use case, you can see atomistic modeling of dopant quantum dot, where you use atomistic package to simulate the tight binding solvers from the device creation. You can use the dopant quantum dot also and find the lowest energy impurity state also. And you can see the DFT simulation with 10,000 atoms. Same atomistic modeling of dopant quantum dot. You can dope your quantum dot also. And here you can see toward multi-scale superconducting qubit modeling. From a atomistic structure, you can move to the classical component. Like capacitance, you can find inductance. After that, you can use QTCAD metal, where chief performance figure of merit. And so this, you can use the finite element simulation to find like capacitance matrix and Maxwell eigenmode. Using our QTCAD software, you can find capacitance matrix and Maxwell eigenmodes. And atomistic simulation for a Joseph Johnson also. Here you can see the capacitance extraction example. You can see the like capacitance extracted using the force voltage and adaptive meshing using our GMesh software. And you can see after that we define the mesh and simulate the result here. And you can also find the Maxwell eigenmode extraction also, where you can use the package of the QTCAD, and you can find the capacitance matrix and eigenmode and extracted fundamental mode, electric field, and manipulate at a ground plane also. And you can see the computational resources here. And you can use the Maxwell eigenmode extraction with adaptive meshing also. And you can simulate single qubit gate simulation. Basically, draw a layout in QScript metal. After that, move to the GMS software where you can render the GMS and create a mesh file. After, compute capacitance with QTCAD software. Here you can see, and solve time evolution with Qt. In the same way, draw layout in the QScript metal and use the GMS software. After that, it will create a mesh file and give to the QTCAD software where you can find compute capacitance and Maxwell eigenmode with QTCAD and solve time evolution. You can see here. You can see the list of publication using QTCAD software here. Multiple paper has been published using our QTCAD software. If you move to the Google Scholar, here you can see a large number of papers has been published using QTCAD software, like this one. 28 nanometer fully depleted silicon on insulator quantum dot transport data taken at 1.4 Kelvin using 3D quantum ticket simulation. You can see the quantum dot device fabricated and 3D quantum ticket simulation using our QTCAD software. You can see a number of papers has been published using our QTCAD software. If you have time, you can read also these papers also to get know more about the software also. I hope everyone received the mail regarding the installation of software and the VS Code and Miniconda and license. I hope everyone installed the QTCAD software. So you let me know. First, we go through the tutorial. Then we go on the hands-on training for the nanowire. Basically, in hands-on training, we go through the Poisson and Schrödinger simulation of nanowire quantum dot, where the primary objective of this simulation, where you can analyze the electrostatic properties and quantum confinement effect in a nanowire quantum dot using Poisson and Schrödinger equation. Basically, when you talk about a nanowire, it is one-dimensional structure with diameter in the nanometer range and length is significantly larger than its width. And we can use the material like aluminum, silicon, and gallium arsenide for insulating material also. And you can see the property like a high aspect ratio, quantum confinement. And when you talk about the quantum dot, it is a two-dimensional nanostructure confined by electron in all three spatial dimensions. And if you talk about the property, you can see the discrete energy level like those of atom earning the name artificial atom, and strong quantum confinement lead to the unique optical and electronic properties also. Here you can see the structure like cross section and cut plane along the channel, like cross section area of nanowire, inner side the channel, then silicon dioxide, then gate, and cut plane along the channel. One end is source and the other end is drain. in between channel is present and source and drain is open. And here in this simulation, we use the two solver like Poisson solver and Schrodinger solver. Basically, Poisson solver calculate the electric potential in semiconductor device and take into account like doping concentration, the number of added impurities in the semiconductor, and applied voltage like gate voltage in transistor. And second one, the Schrodinger solver, basically deal with the quantum mechanical behavior and where you can quantum mechanics like behave waves and not just particle and help us to calculate like electron waves and interact inside the transistor. And we use the QTCAD software at the nanoscale level for the next generation transistor design. If you talk about the flow of QTCAD software, you can see the process. First, we create a mesh generation using GMS software. First, we create a geometry file for the nanowire. After that, we create a mesh file. After that, it is give to the nanowire.python file, where you give the mesh file and define device parameters, material and region, and boundary also like ohmic, source, drain, and channel surface also. And we use the solver like Poisson solver, Schrodinger solver. After that, we execute like mesh loaded and analysis of your uh, device like mesh creation. Here you can see the workflow also. Like first, we create a device specification like select qubit technology. After that, we move to the mesh rendering using GMS software where we define our geometry file for the nanowire and defining some parameters. After that, we will create a mesh file and give input to the QTCAD software. After that, we give some parameters like gate source voltage and other material properties. After that, we analyze the result using pi plot, pi vista, or paraview. Here you can see the workflow. First, we create a geometry file using GMS software, and it will create the mesh file where it consider node coordinates and connectivity and physical group also. You can also give the GDS file and Python file. Using device chain, you can create a mesh file. After that, mesh contain the node elements and physical group. You can assign the material also, region, and boundary also. You can see in material, you define the permittivity, effective mass, and other parameters also, and use in the region collection of elements with material properties. After that, give the boundary like collection of elements with boundary value and method. After that, it will create a device like central data structure where you can assign the parameters of each mesh point at a boundary condition. After that, we use Poisson solver and Schrodinger solver to analyze the result. Here you can see QTCAD model. Like you can give input to the device gen and GMS. So device gen create GTS text file. It will generate using device gen. Give input to the device gen. It will create a mesh file and give input to the QTCAD file. Second option is GMS. With GMS, we create a geometry file. After that, we render the mesh file and give input to the QTCAD software. It means there is two ways to give the input to the QTCAD, through device gen and through GMS. For device gen, you give input like create GTS text file and give input to the device gen, where you can create heterostructure stack and create a mesh file and give input to the QTCAD file, QTCAD software. And second option is GMS software, where you can create geometry of your nanowire. After that, it will render the mesh file and give input to the QTCAD software. And in future upcoming QTCAD version, we also integrate the GY also for a pre-processing and post-processing. And it also comes with atomistic Joseph junction modeling, where accelerate artificial intelligence and VDG solver also, and advanced superconducting modeling, and large-scale qubit simulation also. Now up to you can use 2-qubit simulation and large-scale super quantum chip modeling also you can use. Scaling to the tens of component you can use, and deep coherence model you can also integrate it in future version of the QTCAD software. Let's move to the file and see how to install the QTCAD software. I hope everyone received this type of mail. can see the in upcoming version of software, we also come with the visualization also, like a Jupyter notebook and Python script workflow, where you can pre-processing, post-processing at the same time also in the same window. And if you talk about the comparison between conventional TCAD tool like Silvaco, Center, in QTCAD, it also comes with the qubit simulation, but in Silvaco and conventional TCAD tool, it's not available. Quantum dot simulation you can simulate in QTCAD software, but in Silvaco you can't do this. And value splitting calculation in QTCAD possible, but in not Silvaco. Quantum transport calculation is possible in QTCAD software. You can find quantum transport, Coulomb blockade, and it also supports cryogenic temperature simulation. But when you simulate Silvaco at cryogenic temperature, it's not feasible. And electric dipole spin resonance, it available in QTCAD software. Quantum control, it also in QTCAD software, you can simulate qubit control by external fields and Coulomb interaction modeling also in QTCAD software. Basically, QTCAD is an advanced tool for TCAD simulation. Consider with the quantum physics and semi-classical physics also. They can simulate qubit modeling, spin qubit devices, superconducting circuit, but it's not possible in Silvaco or other TCAD tools. Now let's move to the software installation process and see how to install the software. I hope everyone received this type of mail. First, you have to download the QTCAD software by clicking on this. In the same way, do for the Visual Studio Code according to your operating system. According to your operating system, download the VS Code also. And Miniconda for the Python Environment Manager. Also download the Miniconda. According to your operating system, download the latest one. And move to the folder. First, install the Miniconda. Click on Next. Agree. Next. And you can browse according to a specific location. And move to the next. Next. And click on Install. In the same way, do for the VS Code also. Install the VS Code also. And click on Install. After that, extract the QTCAD zip file and open here. For up to now, I hope everyone completed up to now. Please let me know if someone facing an issue. And open command prompt here by clicking CMD right here. It will open the command prompt. And first check Honda is installed successfully or not by typing Honda version. can see it's the version of Honda 25.90. It means our mini Honda is successfully installed. Now type Honda environment update final file and enter. Type this command and click on enter. It will take some time. Please wait. If someone facing an issue, please let me know.
Excuse me, sir.
Yes, sir.
This is Dr. Balaji Srikanth. Actually, when I was installing Conda, it suggested me that I have to install it for a single user. But I installed it for in my laptop. I changed for all users. So I am not able to type, in the prompt you typed Conda hyphen version,
Yes,
but I'm
sir.
not getting that. How do I go about that?
You can see the path also, like C drive,
Okay.
user, and you can see the mini Honda, mini Honda folder, like mini Honda 3. Copy this path
Okay.
and go in the environment variable.
Okay. I need to set the path in the environment
Yes,
variable,
sir.
right?
Yes,
Okay,
sir.
I'll do that. So thank you, sir.
Now you can type Honda activate QTCAD. From this environment, switch to the QTCAD environment. You can see here. Now type pip install. And type Gmail software. I hope everyone got this type of issue. To solve this issue, we send a Google Drive link in group, WhatsApp group. You can check. and download this GMS file, which is sent to the WhatsApp group. Unzip this and copy the gms.extensor file and go inside C user, Dell, Miniconda, then come to the environment. You can see here environment. Click on this. You can see QTCAD. Click on this. After that, come to the library and paste the license here. Paste the application file here of GMS. Inside the green also paste the license. Paste the application file of the GMS. You can see the path. C user, Dell, Miniconda, environment, QTCAD, library, green. Paste the gms.exe application file here to solve the issue. After that, type pip install GMS.
Hello, sir. I am getting error or not able to install.
Which type of error you get?
Honda, the team Honda is not recognizing the name of CMD let function subscript.
Okay, no issue. After the session, please connect with us. We will solve the issue. For the time being, you can follow the tutorials, follow the session. I hope everyone open the GMS software using command GMS. To open the GMS software, click on File, then Open. And you can see some inbuilt example are given here. Nano background charges.geometry file. Click on this and click on Open. In QTCAD folder, example, tutorial, and mesh file. Like example, tutorial, mesh file. And in mesh file, you can see nanowire background charges.geometry file. Click on this and click on Open. You can see the structure of nanowire. This is a 3D mesh structure. You can see 2D structure also and 1D structure also. Click on File and Save Mesh. Replace. And again move to the command prompt to check QTCAD installed successfully or not. Type cd example tutorials and type here Python background charges.python file and enter. Wait. Close this. Again move to the QTCAD folder and in example tutorial open the command prompt here. First activate the environment. Now run the example. First, select the interpreter first. From the previous code, you can see here QTCAD 3.12.1 QTCAD. Select this. And run this Python file. Please wait 1 minute. I'll get back to you. To check the QTCAD installed successfully or not, you have to activate the environment first. And open the Gmail software. Go to the file, open example, tutorials, mesh file, and you can see nanowire background charges.co file. Click on file and save mesh. Close this image and run this simulation. You can see it started by loading the mesh file. After that, it calculated 3D mesh statistics and solving non-linear Poisson background charges and some Poisson iteration. And you can also see the result also with background charges and without background charges. And you can see the result also. I hope everyone completed up to here. Move to the QTCAD folder. And open a terminal here. And first activate the environment of QTCAD. And open the Gmail software. You can see Gmail software. Click on File and click on New. Go inside example folder. Here you can see QTCAD hands-on. Click on this and click on OK and use Geo extension and built-in kernel. You can see this is a Gmesh GUI. Here you can see File, at a toolbar, Tool, Window, and Helps. At the below section, it comes with the 4 modules: Geometry module, Mesh module, Solver module, and Post-processing module. Click on Geometry module. You can see Elementary Entities. Click on this. Here you can see Set Geometry Kernel. You can see Built-in and Open Cascade. Click on Built-in. After that, click on Add. Here you can see some parameters, point, line. You can add circle, disc, rectangle, plane surface, sphere, cylinder, box, wedges. You can do this. Click on point. Here you can see click on point and give the value 0. After that, in prescribed mesh size point, give 0.3. After that, click on add. After that, give 1.5 in the X and click on add. Again, click on X and give 0. Now, in Y, give 1.5 and click on add. Again, in X, give minus 1.5 and in Y, give 0 and click on add. Again in X, give 0, and in Y, give minus 1.5 and click on add. Here you can see we give the 5 point 0 cross 0, 0, 0, 0 and 1.5. Here you can see also 1.5, minus 1.5 and minus 1.5. You can see 5 point you can add. You can also see in the script form. Here you can see reload script, edit script. If you click on the edit script, it will open in the text format. You can see set factor built-in 0.1, 0, cross 0, 0 and 0.3 mesh point, basically mesh size. After that in point 2, we give the 1.5, then 0, 0 and 0.3. In the same way for the point 3, point 4 and point 5. Again move to the GMS software. I hope everyone completed up to here. If someone facing an issue, please let me know. Okay, now let's move to the next point. Again move to the point and give here 2.5 and 0, 0 and here give 1.5. Mesh size at point 0.15. And click on add. After that, again give 0, then in Y give 2.5 and click on add. Again move to the X and here give minus 2.5, here 0 and click on add. After that give X 0, in Y add minus 2.5 and click on add and press Q from the keyboard to quit the point. You can see. Now you can see here 4.6, 0.7, 0.8 and 0.9. You can also see in the script also 0.1, 0.2, 0.3, 0.4 and in 0.5 and in 0.6 you can see 2.5 and 0.15 mesh size point for the same 0.6, 0.7, 0.8 and 0.9. Again move to the GMS. Here you can see circle arc. Click on circle arc and click on first point on point 2, after that point 1, then point 3. In the same way for point 3, point 1 and point 4. Again click on point 4, then 1, then 5. Again click on point 5, point 1 and point 2. It will create a circle, inner circle for nanowire. In the same way do for the outside cylinder. Here basically click on this point 6, point 1 and point 7. It will create the circle arc in this way. Again click on point 7, point 1, first we create a geometry file for the nanowire, then move to the file, then we'll save the mesh and give input to the QTCAD software. Click on point 8. Again click on point 8, point 1 and 0.9. Again click on 0.9, 0.1 and 0.6. In this way, create 2 circles. You can see in the script also, it create 8 circles, circle arc basically. Again, I repeat the whole process, how to do this. Here you can see point option. First, you have to select kernel. Click on built-in. After that, click on point and give 0, 0, 0 and 0.3 and click on add. After that, give 1.5, then 0, 0 and click on add. You can see 0 cross 0 and 1.5. After that, 0, 0 and here 1.5 and click on add. And for the third point, type wait. Click on reload script and edit script. For point 1 and for point 2, 1.5 and click on add. 0, 1.5 and click on add. Type here minus 1.5, 0 and click on add. 0, minus 1.5 and click on add. After that, for outer circle, type 2.5, 0 and here give mesh size 1.5, 0.15 and click on add. Here give 2.5 and add minus 2.5, 0 and click on add. Minus 2.5 and click on add and press Q to exit. Now click on circle arc. Click on point 2, point 1, point 3. Again do same process for the point 3, point 1, point 4, point 4, point 1 and point 5, point 5, point 1, point 2. You can see point 6 and in this way you can create circle arc. Point 8, point 1, point 9. Click on this. Point 1, point 6. You can see After that, you can see here plane surface. Click on plane surface and click on this and type E from keyboard, type E. You can see it will change to the surface. Do the same for the outer circle. Select and using shift button, click on second circle also, inner circle, and press E. You can see it create a plane surface. Click on mesh and click on 2D. You can see the 2D structure. Now move to the extrude option. Here you can see extrude. Click on this and click on translate. Here you can see for all entities, click on surface. Give the value here for Z. In Z direction, you basically extrude and click on extrude mesh and uncheck this box and select and type E. You can see it extruded. In the same way, do for the outer circle also. Click on this plane and extrude. You can see this is basically source region and source oxide. Let's create for the channel also. Create the channel. Give the length like 10 and increase the mesh by 25. Again click on this surface, plane 30 and type E. And same for the outer circle also. Click on this and extrude. And this is a channel region basically. Channel region and gate band. Again for the source, click 5 and here also 5. Click on this plane 94 and type from the keyboard E. And same for the outer circle also. And type Q from the exit. You can see it created nano Y structure. If you click on 2D, you can see the 2D structure also. You can remove the excess also. And if you click on 3D structure of nano wire, again click on 1D. Now it's time to define the volume and band here. Go to the tool option. Here you can see option. Click on option. You can see geometry. Click on this and click on volume, volume levels, surface and point levels. Close this. You can see the volume also here, volume 1, volume 2 and volume, here you can see volume 5. In this pipeline, you can see your physical group. Click on physical group and click on add. Here you can see add point, curve, surface and volume. Click on surface and give the name like drain band and click on plane 1 and type E from the keyboard. Again give the name gate band and select outer surface. By rotating, select outer surface. You can see select the outer surface to create a gate band and press E. It will create a gate band. After that, give source band and click on this plane and type E from the keyboard, and now you can close this. If you click on this, you can see the name also, physical surface source band. In the same way for the plane one also, you can see it's physical surface drain band. Now let's do the same process for the volume also. Go to the physical surface, physical group, here you can see physical group, and click on volume. And give the name drain and click on volume and type E. Again here give the name drain oxide volume and again click on this volume and type E. Change the name here and give channel. This is channel volume. Click on this and type E from the keyboard. Again give channel oxide and click on this volume and press E. And do the same for the source. Type source, click on this volume and press E from the keyboard and again type source oxide and click on this and press E. Close this and reload the script. Here you can see reload the script. Edit script, you can see here. And you can change here to, for the drain oxide, write 2, and for the channel oxide, click 4 and click on save. Click on 2D mesh and 3D mesh. And click on 3D mesh. Go to the file and click on save mesh. You can also move to the tools and see the statistics also. Like for the geometry also, you can see 36 point, 56 curve, 32 surface, 6 volume and 9 physical group also. In the same way for the geometry and the mesh also, you can see the number of node, points and line also. You can see file and click on save mesh. You can see untitled mesh already exists. Click on replace and move to the file here. Example, tutorials. and hands-on. Here we create a geometry file basically. Move to the VS Code. And in example folder, you can see QTCAD hands-on. Click on this and click on this and give the Python file name nanowire.py. You can see in the QTCAD folder, you can see 4 packages: atom package, device package, qubit package, and transport package. In this first simulation, we go through the device package simulation. In the second, we go through the qubit and transport package also and see the result also. How to simulate the file basically. Let's move to the VS Code and type this Python file. Move to the VS Code and type. First, we import the library basically from QTCAD, device package. We basically import constant as city. After that, we import basically library, some important library which are required to run the simulation from QTCAD device. Import IO. In the same way, from QTCAD device package, we import mesh 3D. Import mesh file. Again, we import some important libraries like for analysis. From QTCAD.device, we import material module. As empty, and after that again some import module like from QTCAD device, we import device module. Import analysis. After that, we import some solver module also from the QTCAD device. Import Poisson and import solver. And name as Poisson solver. And imports also parameters also. Import Poisson solver parameters. Solver parameter as Poisson solver parameters. You can see from the device package, we basically import some packages like a constant. Constant purpose basically to provide electron charges constant value, Planck constant value, Boltzmann constant value, and like elementary charge and vacuum permittivity also. And from the QTCAD device IO, you basically input output to save the file, your input file and output file basically. And and the third module you can see from QTCAD device mesh 3D, you basically import mesh module to represent the discretization of device. Basically, it contains node, element, and physical group like we created in GMS, source band, drain band, gate band, this type. And the fourth module you can see material. It basically used for the material file to import the material like source, for the drain, and for the channel region. And you can see analysis module to plot line cut and slices for the analysis of your parameters basically. And the seventh parameter you can see, we import some solvers from the QTCAD device package like Poisson solver and Schrödinger's Poisson solver parameters also. We import some module first. After that, we subdefine some device parameters also. Define some device parameters. After that, give variable VGS for gate source voltage, like give 0.5 value, and metal work function for the silicon, and energy cap. After that, we define some height for the nanowire and radius also. And give here range like 20. All units are in SI units basically. And assign the radius also for the nanowire. After that, we give the path for the input file and output file here. In the next step, path to mesh file and output file. Here we forget the import path live to use import your path for mesh and output file. Path library here, import. After that, give the directory here, basically script. Path lib. And after that, give the path of the mesh file. And give the file here. Let's see where our mesh file. Here you can see in hands-on mesh file. Our first mesh file. Give the name. Here. First dot mesh and enter. And after that, also give the path for the PTU file to store in PTU format of your band structure. Nanoacademic dot BTU format. You can also store in the text format also, and HRTF5 format also you can store. Now let's load the mesh file first. Load the mesh file here and give the scaling in nanometer, basically. Assign scaling. It is 10 to the minus 9 meters is equal to 1 nanometer. After that, mesh is equal to assign the mesh class and give the constructor like scaling and give the path of your mesh file. After that, we can plot the mesh file also. Plot the mesh file with command mesh.show. If we run this simulation up to now, wait. We forgot to give the name mesh folder also here. Script directory. After that, we have to give the folder name also, like meshes. And do the same process for the video format also. Give the in output folder. It will store in the output folder. Now run this. You can see it plot the mesh file and it divided into the node and region where computation occur basically. The Poisson solver and Schrodinger solver compute here in the node and the region area of the nanowire. Close this. Now let's define the device first. We have to create the device of nanowire. Create the device and give the variable t and device class. And give the mesh file. After that, we have to apply the approximation like Fermi Dirac approximation, and QTCAD offers 3 approximation for the charge distribution like Fermi Dirac, Boltzmann, and Fermi Dirac approximation. With 3 you can use any one like T dot statistic and give here Fermi Dirac approximation. FT approximation. After that, we create a region and assign the material basically, which are created in the GMS software. We assign the like source band, source channel, a gate band, where we have to assign the material also. Like first, we have to create the region first. After that, we have to assign material also. Assign material to region with command d dot new region. We have to assign for the channel oxide also. In single quote, add channel and channel oxide and assign the material file like silicon dioxide. Do the same process for the source oxide and drain oxide also. Assign material also silicon dioxide for source oxide also, and again create the same for the drain oxide also. Now it's time to create the assign the material for the channel, source and gate band also. Assign here material silicon. After that we have to assign some doping also. We assign p doping like 5. Here all unit in SI unit. You have to convert if you want. And doping we have to give 0. Again same true for the drain also. Assign p doping also same 5 E and N doping will be 0. After create the region and assign the material file, now it's time to create a boundaries. Create the boundaries. Now here you have to give the boundary condition. Like you can see here, ohmic band. Click on this and assign here source band. Same do for the drain band also and gate band also. gate band, and you have to assign here the gate source voltage and the metal work function also here. After creating the material, assigning the material file and creating the boundaries, now you have to apply the solver also. You have to create and configure the solver. First, we have to follow the Poisson solver function, import the Poisson solver function. And after that, we have to give some tolerance level also for the Poisson solver. Tolerance level like 1 e minus 5. After that, we have to assign some function like for the device. We have to apply on the device for the nanowire. Poisson solver. And parameter Poissons. After that, you have to apply self-consistent loop, which iterate your Poisson iteration basically. S dot solve. After that, we have to import our array dictionary file where we have to give our potential, conduction band age, and valence band age, and you can plot your band diagram here basically. Let's perform this. We have to give potential in dictionary form. T dot phi comma do the same for the conduction band also. You can see conduction band age. Click on this, and you have to convert from joule to electron volt. For that, we have to divide by elementary charge. And do the same process for the valence band also. After that, we have to save your band structure file. Path and PTU file. After that, we have to assign the array dictionary and give the mesh file. Not equal to operator, assignment operator will be used here. Now you can see. First, we have imported some module from the QTCAD device package. We import some constant module for elementary charge like Boltzmann constant and other parameters, elementary charge. And same way from the QTCAD device package, we import IO module for input output to save output file and input file. And from QTCAD device mesh 3D, we import mesh for defining the region nodes. And you can see here also attributes there. And in the same way, from the QTCAD device, we import material file, import material and as a empty and assign the material here you can see. After that, from QTCAD device, we import device package to create a device for the nanowire. After that, from the QTCAD device, we import analysis to plot the band structure and other parameters also, and plot line cut along x-axis, y-axis, z-axis in this way. And we import one solver. Here you can see Poisson solver to compute the conduction bandage, valence bandage, and their parameters also. After that, we import path life to assign the path variable. You can see here message output folder. After that, we have imported some device parameter. Like first, we give the gate source voltage 0.5 volt and metal work function. After that, height and radius. We assign the height and radius for the nanometer and path to the mesh file and output file. You can see here. After that, we load the mesh file, scaling in nanometer and plot the mesh. You can see mesh.show. After that, we create the device structure with the mesh file and give the static approximation like Fermi direct. You can give Maxwell Boltzmann and Fermi direct. QTCAD offer 3 approximation, Fermi direct and Fermi direct approximation and Maxwell Boltzmann. And you can see create the region. After that, we have to assign the material to the region. You can see for the channel, we assign silicon dioxide. For the source oxide, we also give the silicon dioxide. For a drain, silicon dioxide. And in the same way for the channel, source and drain. For source and drain, we assign doping also. You can see. After that, we create the boundary like source band, drain band, gate band, and give the parameters. You can see create and configure the Poisson solver. You can see Poisson solver function and their tolerance level. After that, we use the iteration, self-consistent iteration. And after that, we assign a dictionary and plot the band structure. Let's run this simulation. You can see it loaded the mesh file first, where Poisson Poisson solver will compute here in this node and region. And you can see some Poisson iteration also happen. There you issue showing. Okay. Let me solve this issue. This is a function basically. And now run this. It loaded the mesh file first. We have to give the function here valence. and run this. We have to plot for the analysis. We have to type also a command to see the band structure, like analysis. Here you can see we imported analysis also from QTCAD device import analysis. To plot, you have to use analysis plot, analysis function dot plot. We have to plot band diagram. And after that, we have to give the device and starting end. And up to 20 nanometers. Give the device height here. And save. And now run this. We write spelling error, bands, basically here band BANDS, not BNDS. And again, now run this simulation. Now you can see the band diagram for the nanowire structure. You can also save in the PNG format at a specific location. And you can also see the BTU format in output folder. In this way, you can plot the band structure, band diagram also. This is a basic simulation where basically we import some important module. First, we import from QTCAD device package. There is 4 package: device package, transport package, qubit package, and atomistic package also. From QTCAD device package, we import constant module, where in constant module, basically elementary charge and other parameters constant value are defined. And from QTCAD device, we import IO for the input, output, and save the file also in like HDF5, BTU format, and BTM format. And from QTCAD device, mesh 3D, we import mesh for defining the region and node. And from QTCAD device, we import material as a empty file. After that, from QTCAD device, we import device. After creation of mesh, we have to convert into device. That's why we import device module. After that, to plot like band diagram and other parameters, we have to import analysis module also. From QTCAD.device, we import analysis module also. In the same way, from QTCAD device Poisson, we import solver as a Poisson solver. We import Poisson solver parameters also. And after that, we have defined some device parameter like gate source voltage and metalwork function and device height also and radius. After that, we have to give mesh file as an input, and we have to save nanowire.btu format in output folder. In the same way, load the mesh file in scaling in nanometer. After that, plot the mesh file, mesh.so.
and create the device. You can see device mesh. After that, we apply approximation. You can see here Fermi Dirac approximation. And after that, we create the region and assign material to the region. Like in geometry file, we created the channel oxide, assigned the material silicon dioxide, and source oxide material silicon dioxide. In the same way, for the drain oxide, we assign silicon dioxide. And in the same way, we create the device also. After that, we create the boundary condition. You can see D dot new ohmic band and give the name source band, drain band, gate band, and you can see here gate source voltage and metal work function on the gate band to create the quantum well. And after that, create and configure the Poisson solver. Give the Poisson solver parameter function and give the tolerance level. After that, we apply the self-consistent loop and analyze the band diagram here. The process will be same for the all. First, you have to import module. Then you can define some device parameter if you want. And after that, you have to give the input and output path file here. After that, you have to load the mesh file. You can convert scaling in any nanometers and plot the mesh if you want. See the structure of mesh file. You can see you can use this function mesh.so. And after that, you have to create a device. And you can give the statistic approximation for charge distribution. You can use Fermi Dirac approximation, Fermi Dirac, and Maxwell Boltzmann. After that, you have to assign material for all region like channel oxide, source oxide, drain oxide, and channel, source, and drain. In source and drain, you can also assign doping also, doping concentration, you can see here. And after that, we create the boundage like D dot new ohmic band and same for the gate band also. After that, we create and configure the Poisson solver parameters and plot the band diagram. The process will be same. First, you have to import modules and after the parameters and give the input output file path, load the mesh file and create the device, assign material, and you can use any solver to find the parameters and you can use analysis module to see the result. There should be 5 processes. First, you have to import modules. After that, if you want to define some parameter, you can do. And after that, you have to import your path file. And after that, you have load the mesh file and create a device. Then assign material. After that, solver and analysis. There are 5 process steps for all the example you can do. You can also follow the documentation. So go to the Nanoacademic. Here you can see the first website. Click on this. Here you can see at the below section of the website, you can see documentation and tutorials. Click on this. And you can see the software. First product, choose the product like QTCAD. And here you can see the installation procedure and getting started, like how to work with QTCAD. You can see the module, the structure of QTCAD API, device simulator with QTCAD device package, transport package, and qubit package. In device simulator, mesh module, you can see QTCAD.device, mesh 1D, mesh 2D, mesh 3D. In the same way, device module, solver module, you can see some solver module. We imported QTCAD device Poisson module. You can also import Schrodinger if you want. If you want strain solver, you can also use strain solver, multi-value effective mass theory solver, labor arm matrix, Schrodinger Poisson solver, quantum well, many body physics, you can see. In the same way for the post-processing, QTCAD.device analysis module to plot quantities, produce slices and line cut. And for the I/O, you can see HDF5 and BTU format. If you go to the tutorials, you can see for the device package, many tutorials are given. In the same way, for the transport package, you can see multiple tutorials are given, like this one. You can see NEGF, non-equilibrium gain function, Poisson simulation of an FDSI field effect transistor with quantum dot. You can simulate this type of structure also, and you can find off state, sequential tunneling, on state, off state, and sequentially tunneling. Charge stability diagram also you can find. In the same way, for qubit package, you can see electric dipole spin resonance. You can find this type of result also. You can see dynamic with noise, and here you can see atom package. If you click on atom package, it comes with the tight binding, and you can see you can also simulate and find a band diagram, band structure of silicon with tight binding model. Here in this QTCAD software, from atomistic to qubit simulation you can do. From atomistic to device to qubit simulation also, from quantum dot region, confinement of electron and holes also. And here you can see superconductor. If you click on tutorials, you can see you can find capacitance extraction of a coaxial cable, capacitance matrix extraction for a small qubit, and Maxwell eigenmode extraction of coplanar waveguide. And you can also use QSKIT metal inside the QTCAD software. It also integrated with QSKIT, where you can simulate 2 qubit gate, 1 single qubit gates, and find the results. And for the Python code reference, you can click on API reference. Here you can see for module QTCAD atom package module, you can see QTCAD atom analysis module. In the same way, for a device package, you can see analysis module. In analysis module, you can use this type of function, analyze dot, like quantum dot. You can analyze, you can get slices, line cut, you can plot band diagram, line cut along z-axis, x-axis, and y-axis. In the same way, for the you can region statistic, save line cut. If you click on this, you can also see the parameters, which type of parameter you have to give. If you follow this documentation, it is easy to use QTCAD software. Here you can see device package. In device package, you can see module. In device module, analysis module, capacitance module, constant module, device module, IO module. You can use KP module also, and labor module. You can see if you follow the documentation, it is easy to use the QTCAD software. Please follow this documentation to use. You can also move to the YouTube. We have curated a video for QTCAD software also. Click on Impulse Technology channel, and in playlist, you can see we have curated a lot of video for all software. You can see QTCAD tutorials, QTCAD project. If you click on QTCAD, Poisson is counting a simulation of nanowire quantum dot, Poisson solver with adaptive meshing, Poisson solver with background charges, Schrodinger equation for a quantum dot, band alignment in heterostructure. In the same way, we created the project introduction, installation for a Windows, and other software also. You can see DFT based software like Rescue and NanoDecal, and for solar cell you can see Laos and SetFos. Let's move to the DS code and again run this simulation again. Create a new Python file here. Click on this and give the name nanowire dot Python file. Again, we have to import up to here. Copy this code because we have to follow same, and in nanowire.python file paste. After that, let's create array dictionary for holes, electron density, potential, and other parameters also. And also do for the electron density. For a hole also and for potential also. Now we have to save the data also. Save path HDF 5 and give the array dictionary. And we have to assign the path HDF5 in path file here also. In outputs folder, for nanowire.h5. After that, also give the path energies to store the energy for path for energy. In text format, and for line cut along z-axis and x-axis. We also plot line cut along z-axis and x-axis. Same for x-axis also. Now move to the below section and save the potential in io.load. We have to load and also save for external visualization. For a para view, if you want to visualize in para view, you have to save in video format. After that, we have to line cut along z-axis, and where x will be 0, y will be also 0 for the same quantities. We have to do for the electron density, hole density, and potential. We have to create array first. And for hole density and for potential also. Now we have to give the name also. And we have to save analysis. Now we have to line cut along x-axis where z will be L by 2. So we have to create line cut along x. Analysis you have to use dot save line cut and give the string, and after that path for line cut along x-axis, then mesh, use array, we have to assign array names, and we have to close. We have to plot also. Plot line cut mesh file you have to give, and after that we have to give the potential region and starting point. Now we have to calculate the confinement potential for a electric potential, and for confinement potential you have to choose the carrier like electron or holes. For choose the carrier you have to use and you can choose electron or holes. I choose electron. After that, set to find the confinement potential, and now you have to give the Schrodinger solver. We have to assign some parameters for the Schrodinger solver. For that, we have to also import module for Schrodinger. You can assign tolerance also and number of state. Like 5, it will give the ground state, first excited state, second excited state, this type of parameters. We have also import solver here from QTCAD device package. And after that, we have to use Schrodinger solver on the device. After that, we have to plot like energy function and self-iteration for the Schrodinger equation. Like first, we have to self-consistent calculation for the Schrodinger solver. Then we have to print the energy also and save the energy in text format. After that, we find the print and quantum dot geometry properties like size, their size properties for a quantum dot. With analysis function, you can see in analysis, find the quantum dot regions. Analyze quantum dot. Analyze dot. Give the device here and true. After that, we have to plot some functions like analysis, for the mass and the potential and electron hole density also. And give the title. In the same way for potential also. Now we have to plot down the state, first excited state and second excited state. To see the band diagram and other structure also you can see, like line cut along X and Z and Y axis also. Now we have to plot ground excited state and first excited state, second excited state. We have to give mass file, then device, eigenfunction, and give the title like ground state, same for the first excited state. Now do the same for the second excited state. and save the file. We have to save the line cut, not energy. And now run this. First, it will load the mesh file. There is some error, like format with we have to change the format for the Python file. Now run this. Sorry. It computed some result like nanowire and BTU format also. After that, it shows some issue like line 77. Let me run this folder. Here you can see same file with the parameters like array dictionary to save the file and plot the ground state, first excited state, second excited state. Let's run this. First, it will load the mesh file. After that, it will find the electric potential. You can see like distance line cut along and band diagram we simulated in previous tutorials. And you can see hole density. You can visualize in also paraview also for better post-processing results. And you can see the potential in orthogonal form. Ground state, you can see. First excited state. Second excited state. And you can see the energy level also. Some Poisson iteration happened. First, it load the mesh file. After that, it calculate the 3D mesh statistics like number of elements and node. After that, it give the boundary level like source band, drain band, gate band, and assign the band like ohmic gate and applied potential. You can see here. In gate band, we applied 0.5 volt. After that, it used the Poisson solver and used the self-consistent loop to iterate the Poisson iteration. And after that, it will save the output in nanowire HDF5 format and BTU format also. Here you can see the geometric property of a quantum dot. And all results will be saved in the output folder. QTCAD example tutorials output. You can see nanowire HDF5 nanowire.BTU format, nanowire band structure.BTU format, and in text format also. You can see the energy in text format. and line cut along x-axis. You can see nanowire line cut x-axis. You can plot in ParaView, Origin, other software, post-processing softwares for better visualization. And you can see nanowire line cut z-axis. In this way, you can simulate nanowire and confine the electron or host using confinement potential function and find the quantum dot region. You can see geometry property for the quantum dot region. In this way, you can create. If anyone have doubt, please ask. I'm audible.
Yes.
Okay. Let's run others example also. In the example, you can see band alignment. Here basically import some library. You can see here from QTCAD device package, import constant module, mesh module, device module, material, and analysis. After that, we import the
Sir, I
mesh
am
file.
facing
Yes, sir.
difficulty in drawing
Yes, sir.
structure in GMS.
Okay. What the issue you are facing? Please let me know. You can create your device through the Python script also. If you are used to the Python, you can create the geometry file of nanowire or any device through the Python file also. It's easy to use. Through GUI, you can easily create the device structure through the point, after the circle arc, and you can also see the script also, like edit script. You can see first we assign the point 0.1, 0.2, 0.3, and 0.5 up to 0.5. Create the inner circle, then outer circle. After that, we extrude. Basically, we stretch the cell. Basically, inner, then outer for the source region, then channel, and then drain. Here you can see we see another example for the band alignment. Here you can see it's take the band alignment.mesh file. To see the geometry of band alignment, go to the file, open, and in mesh folder, you can see band alignment.geo file. Click on this. It's basically 1D structure of a band alignment. And click on the save mesh. It will save the mesh file in the mesh folder. After that, come here and give the path like band alignment.mesh file. It will take the mesh file, and here you can see load the mesh file. You can also use the mesh.show to plot, and after that create the device and add material. You can see here we created a device and use carrier as electrons. After that, we assign the region for a left barrier, well, and right barrier, and assign aluminum gallium arsenide. And for a well, after that, we obtain the band diagram using adhesion rule and confinement potential from the VHI function. After that, we also compare the rescue software with rescue software for a band structure. You can see use rescue simulation input to align band from a atomistic simulation. You can see here. Let's run this simulation. You can see 1D mesh structure. You can see using the adhesion rule band structure. Before setting potential from a PHI. After setting potential, adding potential, you can see. change in curve, shifted barrier height, and band alignment from rescue plus simulation. You can also see from at a atomistic level. You can see ground state, first excited state, and second excited state also. And you can see band alignment from rescue plus simulation at atomistic level, 0.5 electron volt shift in well. Now you can see the ground state, first excited state, and second excited state. You can see the energy level also. Here also. And all result will be same in the output folder. If anyone have doubt, please ask related to the software or any issue related to the geometry file. I am audible.
Yes.
If anyone have doubt, please ask. Basically, QTCAD is easy to use. First, you have to create a geometry file from the GMS software or a device gen, where you have to create give the GDS file. It will create into mesh file and give input to the QTCAD file. In QTCAD file, we have 4 packages like device package, transport package, and qubit package. In transport package, you can find IV characteristic, quantum transport properties, and other parameters also like energy of related functions. And in device package, you find capacitance matrix solver, multi-value effective mass theory solver, lever arm matrix, tunnel exchange correlation function, charge stability diagram, and more. In qubit package, you can find EDSR, electric dipole spin resonance, Rabi oscillation frequency, and other parameters also. After that, atomistic package, here you can see tied binding, where you can use tied binding methods and simulate your material also in the QTCAD package from atomistic to device and device to qubit package, and superconducting circuits also. If anyone have doubt, please ask. You can also write in the chat box also if you want.
Sir, how are you running the codes in VS Code from VS Code to GMAS? Means how the diagrams are drawn there
Okay, sir.
from VS Code.
Let me explain. You have a QTCAD zip file basically, and QTCAD folder. Open a terminal here first, and first you have to activate your environment, QTCAD environment. Conda activate QTCAD. From base environment, switch to the QTCAD environment. You can see here. Now you type GMS. It will open the GMS software. click on File and click on New option. Here you can see folder. Go inside example folder. You can see QTCAD series. Click on, and in mesh folder, give the mesh. Give the name of it. Geometric kernel. Use built-in function. Here you can see here 4 modules basically: geometry module, mesh module, solver module, and post processing. We are using only 2 modules, geometry and mesh. Go to the geometry, elementary entities, and you can see set geometry kernel. Click on built-in. After that, using add, you can use point parameters, circle arc, and plane surface, and extrude function. You can build nanowire. After that, go to the file and click on save mesh. It will save in the same folder where you have created, like QTCAD series mesh nanowire.geo file. In the same folder, it will save the nanowire.mesh file. After that, come to the VS Code, write your code file, like import your packages, and give the path your mesh file. And here you can see you can give the mesh file path here. After defining, you can run this application. At the below section, output QTCAD environment in running condition, basically activated, QTCAD environment activated. You can directly run. Sir, you have to paste a license in save folder, then your user and username, like C user, then Bell, and after that create a folder with name .nanoacademic, and inside .nanoacademic create QTCAD folder and paste a license file. I saw the documentation also. License activation. You can see the here. In this way, you can paste your license file. Create C user, your username, create folder with name .nanoacademic, then QTCAD folder, then in QTCAD inside folder, paste the license.lic file for Windows. And for Linux, you can do the same process. Anyone else who have doubt?
థర్డ్ ఇయర్ వాళ్ళకి 225 ఏదో ఉందండి, 332.5 అనమాట. 1.5 hour ఉంది. కంటిన్యూషన్ ఎగ్జామ్స్ ఎవరికి వాళ్ళకి ఏమిటి దొరుకుతూనే ఉండదు.
Anyone have doubt? Please ask. Okay. Again, I repeat the whole process. How to do?
Excuse me.
Yes, sir.
Sir, I noticed that I cannot use the software offline. It says some license server due to network error. Like, is it possible to use it offline, or is internet connection required?
It is basically network, no network license. You can use it offline also.
So I am getting license error, failed to connect to license server due to network error. Please check your internet connection.
Could you please connect after the session?
Yeah.
Okay. Again, I repeat how to do. First, we have to go inside the QTCAD folder and open a terminal here. First, we have to activate the environment. Conda, activate QTCAD. You can see from base environment, it switch to the QTCAD environment. You can see from base environment, switch to the QTCAD environment. Now type Gmsh. It will open the Gmsh software. If you want to create a new file, click on new. In example, you can create a new folder with any name, and in mesh folder, give the name like new and click on OK and use geo extension and use built-in kernel. After that, in geometry, you can see, sir, please, can you mute? Can you mute yourself, sir? Okay. After that, you have to add point to create the circle, and like here 0 0 0 0.3. Add, you can see here at the here it created the point. After that, you have to give the second point like 1.5 0. And in the same way, you can create with the point and create a circle. After that, go to the file and click on save mesh. In the same path, you can see here QTCAD series meshes nanowire new.geo file. It will save in the new.mesh file in the same folder. Example, QTCAD series in meshes. Here it will save the same file. You can see new.mesh file. After that, come in the VS Code, and you can see in QTCAD series, you can create a new Python file. And you can type your code here in the same way. First, you have to import module. After that, you have to give the path and some device parameters. In the same way, after that, you have to run this and you will get the result also. Let me explain for the inbuilt example. Here you can see for a many body, it's nanowire.mesh file, nanowire.hdf file format. First, I go to this, and first I have to activate the environment. And Gmsh open. After that, go to the file, open. In example, tutorial in mesh file, you can see nanowire.geo file. Click on this, OK. And file, save mesh. In the same path, it will save the nanowire.mesh file. Come to the VS Code. First, you have to import some modules. After that, define parameters and give the path. You can see nanowire.mesh file. And at the below section, you can see QTCAD environment activated here. 3.12.11 QTCAD. Run this. You can see it in the slightly prolonged section. And you can see one electron ground state particle density, one electron second excited state particle. Particle density. And 2 electron ground state particle density, you can see. Anyone have doubt, please ask. If someone facing an issue regarding the installation of QTCAD software, please contact at my numbers. I write in the chat box also. Who are facing related to the geometric creation and other parameters, you can contact regarding the installation of QTCAD software. In the tomorrow session, basically we go through a small presentation. After that, we have created the atomistic stack using device gen, where we have to confine electron or holes, and using the Schrodinger solver, find the eigenvalue and other parameters also. And we also go through the QTCAD method to see how you can create single qubit and double qubit quantum dot also. And we also go through the atomistic capabilities of QTCAD software. Thank you for joining the session. I hope this session is very useful for you. You can use QTCAD in easy way by follow the documentation and video.